This content will show you a brief introduction regarding the polymer and its products. The content will show you the general introduction, properties, classification, and few synthesis of polymers, their applications. Polymers are the smaller molecules which are nothing but the monomers joined together by ionic, covalent, or van der Waals forces, and they form a macromolecules. For examples, they are proteins, nucleic acids, amino acids, which form the basic unit of our body. And that is why a collection of monomers, when they form a new bond, they are called as polymer. The sources of polymers are generally plants, which encloses resins, cellulose, even the milk from the animals, trees, latex, etc. Latex, for instance, rubber is the polymer extracted from the plant resource. We'll go to the properties of plastics, nothing but the polymers. The physical properties, chemical properties, and optical properties of the polymers will showcase how the polymers are being used in various fields. They exist in solid form, gas form, and the liquid form. As they exist in both these three forms, they have vast properties and vast applications. Coming to the physical properties, they have a high tensile strength, and also they do not melt in the low melting point, but when they have a particular melting point, they'll change their state from crystalline to semi-crystalline state. Going to the chemical properties, they have a bond between one monomer and the other monomer using hydrogen bond, ionic bond, van der Waals forces, as already discussed. The reason why the rubber, for example, why it is being elongated, stretched, or whatever the pressure given to it, when they are released, they come back to the normal position. That is why the rubber come back to its original position. It is due to the presence of the van der Waals forces between one monomer and the other monomer. And obviously, the melting point of such rubbers will be very, very high. And the forces, that is the attraction forces between one monomer and the other monomer, is dependent upon its chemical structure. Going to the optical properties, as the polymers have their refractive index with respect to that of the temperature, they can be used in lasers and in many spectroscopic applications. Passing on to the applications of polymers, here are the few points about the application of polymers. Besides these points, you will be having different and various applications of the polymers which are being updated day-to-day life. For instance, polypropylene is a polymer which is used in the case of packaging, in the case of aircrafts, constructions, ropes, toys, etc. The same thing can be applied for the polystyrene, which plays a major role in packaging industry, disposable glasses, plates, toys, containers, etc. Especially the marine containers, they employ polystyrene as their main packaging system. And for the same, it is being used as an insulator also. PVC, which is nothing but the polyvinyl chloride, this polymer, they are being used extensively as the sewage pipes. Besides sewage pipes, they also find applications in many toys and drainage systems. Urea formaldehyde resin is a polymer which has been found in the liquid format, and it is used for making adhesive molds, laminated sheets, etc. For making paints, coats, and lacquers, glyptal is a polymer being used and employed in day-to-day life. Bakelite is another polymer which is used in the kitchen products, toys, jewelries, firearms, computer disk, insulators, etc. Now we'll pass on to the polymerization. Polymerization, from the name itself, you can just grasp the point that it is a reaction process from which two or more number of polymers connect together to form a big polymer chain. Under polymerization, you will be seeing two processes. First one, it is the addition polymerization, and the next one, it is the condensation polymerization. In this process, addition polymerization is the one wherein the monomers will generally have individual double bond, and they will be converted into the single bond to form a uniform chain. And this is the process which is involved in the addition polymerization. That is, merely the monomers will form a single bond linkages. Whereas in the case of the condensation polymerization, that is two different monomers, they will combine together to form a big polymer chain, through which there will be elimination of molecules. Elimination of the molecule is that, for example, you will be having water, HCl, ammonia, or alcohol. In the addition polymerization, there will be a single bond formation between one monomer and the other monomer. Example, you can have polyalkenes, polystyrene, etc. Then we'll go for the condensation polymerization. Here is the example given. It is nylon. In nylon, there will be a combination of two monomers, adipic acid and the hexane diamine. Here in this polymerization, there will be elimination of water molecules, so that the nitrogen and the ketonic group of your adipic acid will form a bond, so that you will get the nylon group as the polymer. This is the flow chart which represents the classification of polymer. Classification of the polymer can be based on many parameters. Here are the basic parameters given under the heads: based on the origin of the source, based on the structure, based on the molecular forces, based on the mode of polymerization, and based on the composition. Under these classification, we had already seen about the mode of polymerization, addition polymerization and condensation polymerization. Now we'll start with the origin of source. Under origin of source, you'll be having three sources: natural polymers, semi-synthetic polymers, and synthetic polymers. So from origin, the polymers can be directly extracted from the natural source, which is nothing but the trees, animals, etc. And synthetic polymers are completely extracted from the laboratory. The second synthesis is that the semi-synthetic polymerization, which will have the combination of 50% of from the natural resources and 50% which will be continued from the laboratory. The next one, based on the structure. Any monomers, when they form a bond, they may form a bond linearly. That is, they may have end-to-end bond formation, which will come under the linear polymerization. The next one, it is the branched chain polymers, is that with the linear polymers, they'll just have one or two branches, so that through those bonds, they will form a bond with the other neighboring monomers. The third one, it is the cross-linked polymers. Cross-linked polymers are those, for example, rubber. They'll have the cross-linked polymers. That is, they'll be having a network-like structure, so that they'll be having a high network structure, high bonds between one monomer and the other monomers, and they will come under the category of your condensation polymers. The next one is based on the molecular forces. You'll be having the four types of polymers: elastomers, fibers, thermoplastics, thermosettings, which we'll be seeing in detail. Then the last classification is based on the composition: homopolymers and copolymers. Homopolymers is that the monomers will be having uniform structure. That is, the first monomer will be same as that of the 100th polymer. Whereas in the copolymer, you'll be having the different structures. Now we'll detailedly go to the classification of polymer. The first one, it is based on the source. As we have already seen, the natural polymer will have the source directly from the plant or the animals, their latex, from their cellulose, from their DNA, etc. Then semi-synthetic polymers they'll be partially obtained from the natural source, partially from the laboratory. For example, it is rayon. and viscous rayon, etc. Synthetic fibers are completely extracted from the laboratory. Example, nylon, terylene, polyethylene, polystyrene, etc., etc., etc. The rubber, it is the common polymer which can be either extracted naturally, and also it can be synthesized completely from the laboratory. Next, we'll go on to the based on the structure. Under the structure, as we have already explained, linear polymer is that one monomer and the other monomer, they'll have a simple single bond. They'll form a single bond structure between one monomer and the other monomer, and they'll form a chain. Example, polyethylene, nylon. These kind of polymers, they'll be having low melting point, which is attributed to their structure. The second polymer is that the branched polymer, their melting point will be slightly higher than that of the linear polymers. And so as to the cross-linked polymers or network polymers, their melting point will be higher than that of the linear branched polymers. For example, rubber, bakelite, resins, they will be having a network-like structure. So as to melt all those monomers, it will take time, and that is why the reason is that they will be having high melting point. This can also be explained in other words is that linear polymers will be harder, branched polymers will be slightly higher than that of the linear polymers, whereas the cross-linked polymers will be the hardest form and it will be very rigid and brittle. This can be studied from the structures which are given below, the linear, branched, cross-linked and the network structure. Next, we'll pass on to the polymerization, addition polymerization and the condensation polymerization. As it is given in the distinction points, under addition polymerization, the monomers will be having double bond. When they polymerize, they'll form a single bond so as to bond with the nearby monomer. Whereas in the condensation polymer, they'll be having one monomer and the other monomer, they will form a polymer chain so that they'll be removing a byproduct as water, HCl, alcohol or ammonia. So this is the main difference between the addition and the condensation polymer. From the structure itself, you can inquire that the molecular weight of the addition polymers will be lower compared to that of the condensation polymer. Examples of your addition polymer is that the Teflon, polyethylene, polypropylene. Condensation polymers, for instance, nylon, polyesters, polyurethane. Passing on to the classification of polymer based on molecular forces, you'll be having 4 striking polymers: elastomers, fibers, thermoplastic polymers and thermosetting polymers. They all will be having a high mechanical properties which has good strength, good elasticity and good toughness, and all will be having a brittle property. First one is that the elastomers, they from the name itself you can find out the property being elastic. That is, the one monomer and the other monomer, they'll be having weak van der Waals forces so that you can elongate the monomer, and if you release the pressure, they'll come to the exact position. So that is the beauty of the polymerization that takes place under the elastomers. Rubber is a very good example, and the neoprene, Buna S, Buna N, they are the good examples of your elastomers. That is, the monomers, they'll be having a bond which is weak van der Waals forces. They'll form a polymer chain, and if you find any pressure, they will elongate, and if you release the pressure, they'll come to the exact position. So this is the beauty and the striking beauty of the polymers, which stands distinguished from the rest of the polymers. Passing on to the fibers, the example is that nylon, the wires which we use domestically, they are the example of your fibers. They have good hydrogen bond between one monomer and the other monomer. So that is the hydrogen bond being involved in the intermolecular forces between one monomer and the other monomer. Nylon finds vast application in your textile industries. Then coming to the thermoplastic and thermosetting polymers. Thermoplastic polymer is that they'll be having high intermolecular forces between one monomer and the other monomer. If you heat a monomer, that is, if you heat any polymer, they will get their good shape, whatever the shape we desire. And if you wanted to make the polymer to whatever the shape you want after it gets set, and that polymer will be possible. Whereas in the case of the thermosetting polymer, if you wanted to make into a particular shape, you will have to heat and the particular shape will be attained. If you remove the heat, that polymer will not go into the initial shape. So that is the striking difference between thermoplastic polymer and thermosetting polymer. Clearly, the difference is that if you heat a polymer, they will go to a particular shape, and if you remove the heat, it will come back to its original shape. That is thermoplastic polymer. And thermosetting polymer is that you cannot return the polymer to its normal shape when you remove the heat. So that will come under the thermosetting polymer. We'll see the detailed diagrammatic representation of thermoplastic and the thermosetting polymer. Simply, the thermosetting polymer, you can have the example by using the egg. Egg is nothing but the DNA protein which is present in the liquid form. If you make it into an omelette like structure, it will come into whatever the particular shape you're cooking. And after, if you remove the heat from the food, it will not revert into the initial structure. So that is a polymer which will come under the category of your thermosetting. Whereas the thermoplastic, this you can take the example from the butter. If you heat the butter, it will get converted into the ghee, and if you remove the heat from the ghee, it will get converted into butter. So that will come under the category of your thermoplastic and the thermosetting polymers. Next, we will pass on to the composition, homopolymers and copolymers. Homopolymer is that all the monomers will be uniform and they will be connected between one monomer and the other monomer using a linear polymerization, nothing but the addition polymerization. Going to the copolymer, in other words heteropolymer, the monomer will be different from one monomer to the other monomer, and the two monomers or the three monomers, they can be arranged in uniform format, that is A and B monomer, they can be arranged in whatever the shape it can be. So it is diagrammatically represented here. It can be random copolymer, alternating copolymer, block copolymer, graft copolymer. So we'll see some examples of the polymers which we have discussed earlier. For instance, we'll start with polyester. So polyester is a good example for your condensation polymers. Here the two monomers given here are ethylene glycol and the terephthalic acid. So these two monomers will combine to form a polymerization, that is condensation polymerization. Here there will be a removal of water molecule. From the ethylene glycol there will be removal of hydrogen, and from the terephthalic acid hydroxyl group will be removed, combined as the water molecule, so that the oxygen from the ethylene glycol will directly connect with your ketonic group of your terephthalic acid, so that a condensed polymer will be formed, nothing but your polyester, polyethylene terephthalate. The properties are very vast. It is a crystalline compound. It can be easily washed, easily dried. It finds many applications in textile industries, which has high mechanical and electrical properties. It can retain its shape, and it can be used both as the thermoplastic and thermosetting polymer. And uses of the polyester goes in all the forms of textile industries, and few of the applications are given here. Now we'll pass on to the next polymer, polyvinyl chloride, which is commercially called as PVC. Here this polymer is a good example for your addition polymerization. There is no removal of any byproduct. Here, a double bond is getting converted into a single bond, and hence there will be the formation of polyvinyl chloride. Properties of polyvinyl chloride is obvious. Everybody knows that it is very rigid. It has good mechanical property. It is an insulator. It will not conduct electricity. It is insoluble in water. It is insoluble in acids, and it is non-toxic. And that is why this particular polymer finds various applications. And it's also cost effective. Here are some applications of PVC given. Even in the medical applications, besides your sanitary purposes, PVC finds application in many packaging, arts, designs, constructions, etc. Here are some examples for your view: polystyrene compound. Now we'll pass on to the important polymer, Teflon. Here, this poly tetrafluoroethylene, this is a good example for addition polymerization again. And then here, the double bond is getting converted into a single bond, which forms polytetrafluoroethylene. So this is a common structure, and from the previous explanations, you can imagine the 3D structure of your Teflon, which is chemically called as polytetrafluoroethylene. Uses and properties of Teflon is that though they can be bent, though they can be malleable, they are resistant to few of the chemicals. That is, they seem to be unaffected by ozone, chlorine, acetic acid, fluoric acid, hydrochloric acid, etc. And they are find good application in the case of the mechanical industries. That is, they can be used as a coating in the case of automobile industry, so that it can protect a particular automobile from extreme heat or from the extreme lower temperature. And it is also can withstand temperature up to 260 degrees Celsius, and it can also protect from any of the weather conditions. Here are some properties for your view of the Teflon. Some chemical properties, notable chemical properties are: they are resistant to corrosive agents, they are non-inflammatory, non-adhesive. Some some electrical properties are that they have high surface resistivity, low dielectric constant. And it is obvious that their mechanical properties are flexible, and that is why they can be coated in the case of the automobile industries. Here are some physical and thermal properties which has been explained earlier. Some of the applications of the Teflon are given here. They can be used as a personal care products, home and gardening products, carpets, and even in the athletic shoes. Now we'll pass on to the last polymer, rubber. Here is the diagrammatic representation of the synthesis of rubber, which gives you two monomers. The first monomer is butadiene and the second monomer is styrene, which undergo polymerization in the presence of sodium. You have to heat both these monomers, wherein you can form a good polymer chain, wherein there will be connection between the CH2 group from your butadiene, that is the end product, with that of your styrene. Here the double bond from butadiene and the styrene will get converted into a single bond, and this is a good example for your addition polymerization. And the properties of the natural rubber are been earlier discussed under the head of your elastomers, and again for your view you can see the properties of the natural rubber. It is rigid, it is highly soft at times when it is heated, and it is highly not affected by water, acid, alkali, etc. It has low melting point and low tensile strength. It has good elastic property, and if it is heated, it can go to the desired shape, and if you wanted to make it to the revert to the exact position at the starting point, you can remove the heat. And it is coming to the oxidation property, it can be oxidized by oxygen and ozone. These are some chemical properties of natural rubber. Some of the diagrammatic representation of some of the rubbers which is updated applications Even in the healthcare automotive field, it can be used. Application of rubbers. This is the view for which you can use the rubber. For instance, foam rubber is used in making pillows, cushions, mattress, automotive pads, which actually replaces the usage of cotton. And due to its elasticity, it is used in golf balls and in tubes of some automobiles. It is used as a solid propellant fuels in rocket motors. And here are some other extended and updated applications of your rubber. Thank you.